Hello, guys. I hope y'all are doing well. I'm going to start with the first lesson, 4.3, and then I'm going to continue to put stuff throughout the next 3 weeks because, as you know, we will be closed till after spring break. I will not post anything that is, I will not post anything for you to do during spring break. But for the next 3 weeks, we're going to do a few lessons. We're going to do 4 lessons, and this will be the first video. And they're going to be not very long videos, as I'm just going to do each video by page. And so this is be video for 4.3 for page 1, and then the next video will be 4.3 page 2. Again, nothing will be graded throughout these 3 weeks, but what will be is expected is that when we come back, that you've had that take-home quiz, the section 3.1, 4.1, and 4.2 quiz. Alright, well today what we're going to talk about are homogeneous linear equations with constant coefficients. So these are differential equations where beside each differential, you're going to have just a constant. So there's not going to be functions in front like a of x, p of x, q of x in front of y, y prime, y double prime. And so the first thing that we're going to talk about is we're going to talk about a homogeneous linear differential equation with just constant coefficients, but of the first order. And so here you see we have a y prime plus by equals 0, where a and b are going to be constants. Now, if a and b are constants, then there are really 2 ways to solve this. We could solve this by separable equations, where we can separate the variables, or we could solve this with an integrating factor. Now, when we say I want to solve this with separable equations, the first thing that I would do is I would move everything that doesn't have a y prime to the right side. And so this is what I'd have. I'd have y prime is equal to negative b over a y. And one thing that we know is that negative b over a is also going to be a constant. So I'm going to change this to y prime equals ky. And based off of this, we know that we've solved the separable equation quite a few times. So where our solution is going to be of the form y equals e to the kx. Now, when we're dealing with nothing but constant coefficients for our differential equation, what we're going to be able to do is we're going to be able to substitute this in for y equals e to the kx to make our differential equations a little bit easier to solve. And in the text, in most differential equation textbooks, instead of writing it as your solution to this differential equation as y equals e to the kx, again, I know there would be a c sub 1 in front because there'd be a constant, but most texts will write it as y equals e to the mx. Right? Now, for solving first order homogeneous linear differential equations with constant coefficients, one way to do this is to make our work a lot easier by substituting in for y e to the mx, because we know that will be a solution. So for our first order differential equation here, we have y, but we need a y prime. All I need to do to find my y prime is to look at y equals e to the mx, take the derivative of that, y prime equals, and then I have m e to the mx. And then what I can do is I can plug in to my first order differential equation with my y prime and my y, so that I get a y prime plus by equals 0 as a m e to the mx plus b e to the mx equals 0. After doing that, I can pull out an e to the mx, and I get a m plus b equals 0. And solving this, I know that e to the mx is never going to approach 0. And so I know that the only way that I would have a solution is if I have am plus b is equal to 0. So I just set a m plus b is equal to 0, and I'm able to find my solution. M is equal to negative b over a, and then my solution to the first order differential equation would just be y equals e to whatever m is. In this case, it's negative b over a x, and there's my solution to the first order equation. So using this and using the substitution of y equals e to the mx and y prime is equal to m to the e mx, that's an m. It's kind of hard to see on there. I can solve this first order linear differential equation. All I would need to do is substitute in my y prime and my y. So I'm going to have 3m e to the mx plus 2e to the mx equals 0. I'm going to pull out the e to the mx, and I get 3m plus 2. And again, I'm not going to always show this part where we just pull out the e to the mx, set that equal to 0. So now again, I know this is not going to approach 0, so only my solution would be found here where this equals 0. So I'm going to set that equal to 0. 3m plus 2 is equal to 0. Subtract 2, divide by 3. M equals negative 2 over 3. So then my solution is just going to be y equals e to the mx. So y equals e to the negative 2/3 x. And there's my solution. And my general solution would be y equals c sub 1 times e to the negative 2/3 x. So there's the general solution. All right, moving on to the auxiliary equation. So what we can do is we can take this idea and apply it to not only first order differential equations with constant coefficients, but also second order and beyond. So when we plug it into this second order differential equation, we're going to substitute once again our y equals e to the mx for our y prime, and our y double prime. So the first thing we need is our y prime, which again, just take the derivative, and we get m e to the mx. And then we need y double prime because it's a second order differential equation, and we get m squared e to the mx. Substituting that into our differential equation, we get a m squared e to the mx plus b m e to the mx plus c e to the mx. Set that equal to 0. And then we can pull out the e to the mx. We pull out the e to the mx, and what we're going to be left with is a m squared plus b m plus c. And that equals 0. And notice once again, this will not be able to, this is not going to equal 0, so therefore our solution is going to be found here, which looks like a quadratic equation. And so to find our solutions, all we have to do is once we see this quadratic equation, we can solve for m where it equals 0, and therefore we'll be able to find our solutions. So that gives us the auxiliary equation that am squared plus bm plus c equals 0. All right, now there can be 3 cases for this. The first case is where we actually get distinct roots. So say we have our quadratic equation. We've already substituted our m's, and we get am squared plus bm plus c equals 0. And then we factor it to find the solution. So say we factor it, we found some solutions, or we can always use the quadratic equation. So say we solved for m using the quadratic equation. M equals negative b plus or minus the square root of b squared minus 4ac all over 2a. In the case of getting distinct real roots, what will happen is that our determinant, our expression underneath the radical, has to be greater than 0. So b squared minus 4ac is greater than 0. So this means that we'll get two distinct real roots. And so we'll find two solutions. We'll have m sub 1 and m sub 2. All right? And so to find our first solution, y sub 1, is just going to be e to the m sub 1 x. To find our second solution, it's going to be e to the m sub 2 x. And to find our general solution, is just y equals c sub 1 e to the m sub 1 x plus c sub 2 e m to the m sub 2 x. And there's our general solution for distinct real roots, so two different real roots for our equation. Now, what happens if we have repeated real roots? So that when we use the quadratic formula again for a m squared plus b m plus c equals 0, we do the quadratic formula, we get negative b plus or minus the square root of b squared minus 4ac all over 2a, where what's underneath our determinant is going to be b squared minus 4ac. That's going to equal 0. So that means that our m sub 1 and our m sub 2 are going to equal each other. So our m sub 1 is going to stay the same. M sub 1 is going to be e to the, our first solution. So y sub 1 is equal to e to the m sub 1 x. Now to find our second solution, we'll just go back to reduced orders because we found the first solution. We'll substitute that back into our original equation. When we do that, what's going to always be the case for our y sub 2 is going to be our y sub 2 is just our y sub 1 but with an x in front. So x times e to the m sub 1 x. And the way to do that is just going back to reduced orders from our last lesson, so 4.2. And this is what we'll get for our second solution. So therefore, our general solution is going to be y equals c sub 1 e to the m sub 1 x plus c sub 2 x e to the m sub 2. I'll say m sub 1 x. I could say m sub 2 because they both equal each other.